Autonomous vehicles, smart cities, and drone swarms are some of the emerging technologies that rely on AI video processing. But can our infrastructure handle even more video when it already makes up 80% of internet traffic? What happens if you add fleets of driverless cars, each streaming from dozens of high-resolution cameras non-stop to servers and each other? A buffering Netflix stream is a nuisance. A buffering drone swarm could be a national security threat. To enable these technologies at scale, we must radically rethink how video is transmitted for AI processing, especially when humans will never view it. That's why a different kind of video codec is needed. OP Solutions, in partnership with Florida Atlantic University, is leading the way. I'm here at Florida Atlantic University's Multimedia Labs to see the first real-time implementation of a new video compression standard called Feature Coding for Machines, or FCM. As more video is consumed directly by machines, traditional codecs are becoming a bottleneck. They waste bandwidth, they increase power consumption, and they limit the effectiveness of the machine learning tasks. FCM solves that. Here's how. Traditional codecs compress every pixel to preserve details that matter for humans watching a video, but not for AI. This creates high bandwidth streams that drain battery power, waste network capacity, and still fail to deliver accurate object detection, all of which are serious limitations for edge devices. FCM takes a different approach. Instead of transmitting pixels, it keeps only the information required by the AI. It does this by intelligently splitting the workload between edge and server. The edge device runs the first stage of a neural network locally, generating intermediate features that are compressed and sent at a fraction of the bandwidth required by traditional codecs. The server then completes the task, enabling lower power use and more accurate results. So how does FCM compare to the effectiveness of traditional codecs in object recognition and similar tasks?
In peer-reviewed tests, we found that FCM delivers same or better object recognition accuracy compared to VVC while taking 73% less bandwidth.
The comparison of FCM to the most commonly used video codec in the world, AVC, also called H.264, it's even more stark. In our testing, FCM achieves an astonishing bitrate reduction of over 90%. As you can see in the chart, an H.264 bit stream that requires bitrate of 100 megabit per second to detect objects reliably, it'll now need less than 10 megabits per second to do so with FCM. FCM or a similar technology will probably be required for scalable operation of autonomous vehicles, drones, and other mission vision use cases, particularly in areas with inconsistent metered or limited bandwidth. Regarding object detection, FCM is also excels here. Each point on this red distortion graph shows how much bitrate is needed to achieve certain position of the tasknet. FCM, the orange curve, always achieves much better performance than VVC, also known as H.266, at the same bitrate. And VVC requires a significantly higher bitrate to achieve the same level of precision. More specifically, as the table shows, at similar bitrates, FCM enables object detection between 50 and 70% more reliably than VVC. We excluded AVC from this comparison because at many bitrates, it simply does not support reliable object detection.
Here's FCM in action. On the upper left is a video showing what an edge device, in this case a robot dog, sees when following a human. The center displays what an AI running on the dog has extracted from the video, specifically the features, which comprise the bitstream from the dog to the server. As you can see, because the bitstream carries only features, not full image data, it's inherently more privacy preserving than traditional video. After processing, the server identifies the human, the pink shape on the bottom right, and signals the dog to follow. Dr. Calva explains further.
In the full server view, you see processing that runs at high frame rates in real time at bit rates under 100 kilobits per second. Frame rates at this level are important for machine vision use cases that need to react quickly to detected objects. Reliable object detection at these frame rates would require over 70% more bandwidth with any other available codec. This could mean the difference between an autonomous vehicle swerving to avoid a falling tree on a mountain road and hitting it. Even an edge device with a lightweight CPU like this dog can extract basic features from the video, segmenting objects into human or not human. If the edge device includes a standard issue GPU, implemented here using a Lenovo laptop, the FCM bitstream can include a richer set of features, tracking more object types at much higher speed.
What's cute in a dog demo has serious implications. Drone swarms, for example, need to share video streams, conserve energy, and operate in places with unreliable internet connectivity. With traditional video codecs, communication breaks down after a handful of edge devices. FCM makes it scalable, enabling many more devices on cheaper hardware. FCM also allows edge devices to dynamically adjust the degree to which they compress the video. A drone with FCM can compress the video more if there's low bandwidth available, and less if it needs to conserve power. Likewise, FCM enables widespread deployment of autonomous cars. These vehicles rely on 8 to 12 cameras each. Inside the car, that level of data flow can be manageable, but vehicle-to-vehicle and vehicle-to-server communication using traditional codecs would overwhelm network infrastructure in many places, with potentially life-threatening implications. If we want to safely deploy fleets of autonomous vehicles, we will need to use FCM or a technology like it to make these communications much more efficient. FAU has contributed to both traditional video compression standards and this next wave of machine-centric technologies, giving them a unique perspective as this technology evolves.
Working with OP Solutions, we have contributed core tools to the FEM standard, several of which are now part of the official MPEG reference software. We're also the first to implement real-time FCM in a working system, and we are writing the official FCM reference manual, which will be published by Springer. Because FAU and OP Solutions have been so deeply involved in FCM standard setting, we're positioned to refine our implementation through the committee draft stage in October 2025 and the draft international standard stage in January 2026, culminating in a fully compliant product launch alongside the final version of the standard in July 2026. OP Solution is already in discussions with potential partners about funding and support for productization, as well as the development of FCM version 2, expected to begin shortly after July 2026.
So while the standard is being finalized, the technology is already working and deployed in real time and ready to solve one of the biggest bottlenecks in scalable AI, making the video data lightweight enough to move and process efficiently. For more information or live demo, please contact OP Solutions.